So now you have a lot of practice computing asymptotic bounds, which means those big O classes for various pieces of code, when we're thinking about a piece of code that's executed on a given input. But what we'd like to do is step back and think about our original problem. And our original problem was measuring the performance of an algorithm, which was a strategy for solving a problem. And so that means that we don't want to just focus in on a single input. We want to think about how the algorithm behaves for all inputs. And so by the end of this video, you'll be able to define what it means to talk about the worst case, average case, and best case performance of an algorithm, and talk about how that really talks about the various inputs that we might have to come across. And then we'll talk about also why each of these is used. So let's think back to this big picture we have of an algorithm as a problem-solving strategy or machine that takes some input and produces output. And the performance, well, that we've been focusing on is the time that it takes for the algorithm to do this, to report back the answer given the input. So in the example that we've talked about way back when we first started, we were looking at the has letter method, which took as its input a word, which was a string, and a character, which was the letter that we were looking for in that word. And then it returned either true or false based on whether the character was found inside the string. Now, as we saw when we were counting operations, depending on the specific word and letter combination, our algorithm behaved a little bit differently. It took a different number of operations in each one of these cases. So even if we were looking at the exact same word, so that a fixed length word and one character, we weren't changing the number of characters we were looking for, we could still have quite different behavior in terms of the number of operations that our algorithm required before it could output the answer. And so what we'd like to do now is capture that variability in terms of the algorithm runtime and talk about the different contexts we might care about. So we might be optimistic and say, in the best possible case, how short might be my wait? How quick might my algorithm be? So if I give the algorithm just like the most beautiful input, whatever beautiful means, then how quick can it respond to me? And now still this input is going to be of a fixed size n, so we don't expect the algorithm to be very quick no matter what size input we have. So we're just thinking about within all the inputs of size n, what's the best possible behavior of my algorithm? And so thinking back to the has letter method, when is this algorithm the quickest? When does it have to run very few operations? Well, think back to what we do. We start at the beginning and we look for our letter in every possible position of our string. So if we found our letter at the very beginning, if our letter was the very first letter of the string, then we'd be able to quit while we were ahead. We'd be able to return out of the method very quickly. So the best case for this method is when the word that we've input starts with the letter that we're looking for. And in that case, well, this algorithm just really needs to do one check, really. It just compares the letter that we're looking for with a character at the first position of the string, and that takes constant time. So in the best case, this method is a constant time method. Okay. So that's interesting, but most of the time we're not going to be in the best case scenario. Most of the time the word that we care about will not start with the letter that we care about. And so this is just a very small view of how this algorithm behaves. This is one special case. And so on the other hand, we might be pessimists and say, well, I think things are going to be bad. I think my algorithm is going to take forever. And so what should we prepare ourselves against? What's the worst possible performance of the algorithm, no matter how bad the input, still for a given fixed size? And so what we'd like to do now is look at our algorithm and say, as pessimistically as possible, in the worst possible situation, how many steps will I need? And so, again, with our example of has letter, what's the worst possible situation we might have in terms of runtime here? Well, we're stepping through the letters of the word, and each time we're looking for our desired letter. And so in the worst possible situation, what we're going to have to do is go through the entire word and either just find our letter at the very end or not find it at all. So the worst case for this method is that the letter that we care about is either at the end of the word or it's missing altogether. And in either one of those situations, what happens is that we've stepped through the entire input word and only are able to return our answer to the user once we've looked at all of the characters in the string. And so in either way, what we have to do is some constant number of instructions for each position of the each position in the word. And so that means that we need to do big O of n much work, where n is the length of the word. And so in the worst case, where we have to go through the entire string, this method takes linear time, big O of n time. Okay, so we've got the best case situation, we've got the worst case situation, and just if we think about the meanings here, the amount of time our algorithm takes in the best case will always be shorter than the amount of time our algorithm takes in the worst case. Okay, and so when we think about this best case and worst case analysis, it's useful to keep in mind why we might care, how we'll use these bounds. And so you can think about the best case analysis as this, this guarantee that we'll always have to spend at least this amount of time doing this algorithm. We know that we'll never be shorter than the best case. Okay, and so if we're budgeting our time, we know that we have to budget at least this amount of time. Okay. For the worst case analysis, we know that we've got a guarantee that we'll never have to wait longer than the worst case analysis to get back an answer from our algorithm. And so if we're planning ahead, we'll know that by a certain amount of time, and maybe before, we'll have terminated this algorithm. And so it's useful to have these extreme situations analyzed when we're trying to analyze how our algorithm is going to behave, no matter what input we get. Now we've understood the extremes. Thing is that in real life, we don't usually live in the extremes. We often live somewhere in that messy middle. And so we also have a notion of average case performance. And with average case analysis, what we'd like to do is get a sense of the performance of the algorithm on average if we consider all possible inputs of size n. Now, this gets really messy. All sorts of considerations need to get taken into account. If we want to be completely precise about it, we need to think about the distribution of possible inputs, how likely it is to get different kinds of inputs. We can also think about what happens with each of those inputs on their own and then try to put them together. As you can probably tell, this is very messy very quickly, and what we typically do is just say average case we realize is more realistic, but it's too hard, and we're going to use the bounds that we got from the analysis of best case and worst case to give us the ballpark, understand the sandbox in which we're playing, and that's good enough. So there we have the best case, the worst case, and the average case possibilities. Notice that we're using the asymptotic notation, the big O notation, to describe all of, in each of these contexts, what the runtime of the algorithm is. But what we're computing is going to be a little bit different in each situation.